So my talk today, I will inspire some talks that I have seen in this year from ATT, from Google, from NVIDIA. And I think that my talk will be a little bit motivational for you guys to know more about AI, mainly deep learning. Also, I will show some code and some math, because as a professor, I love to show math and code. Amanda knows that. And this first step on my talk about inspired in an ATT presentation called the Road to 2025. Yes, we have a routine with new technologies like morning routine using augmented reality. And the first time you get morning workout, you complete personal trainers with wearables using measures about health metrics. Also, you can see your news at morning using your wearable glasses with augmented reality or virtual reality, and go to the work using your autonomous car or your autonomous driving. At the nightlife, you can meet your friends for a game after work, using your augmented reality to find your car, to find your lift, find your friends at the station or at the game. Also, you can see replays of the game using your cell phone, looking for the video, the replay. So you have a very rich content, box applications and development over here in this road to 2025. Also, using your smartphone, you can connect with your friends using also augmented reality, video streaming, watch concerts and play music around the road. At the point of view in industry, we're calling about more advanced technologies with low latency 5G, with telemedicine, with widespread remote surgery become very common. AR can help the bridge between knowledge and skills between the workforce and the managers. And also we can see about transforming the shopping experience with a lot of information over here. And then we have the 10 technology disruptors, and we can see something common of them. We have the 5G as the first, a very special term, edge cloud, the AI and machine learning evolving in a distributed way. Open source, that's the core of the machine learning today, because we're talking about new algorithms, new models, and new databases that must be open sourced for the great adoption of the technologies. And also other technologies like Internet of Everything, robotics, personal assistance, virtualization, virtual augmented reality, autonomous drones, and cars. And at the core, we have AI. AI and open source, I can talk, they work together, and game changers also in the scenario of 5G. When we talk about 5G here, it's about connection, integration with the cloud. Then we have 5G and the edge, the connection between the servers in the cloud and another point, the Internet of Things. And we have some points like real-time network, because how today you think about real-time, autonomous driving is about real-time, billions of devices working together. Intense computer, the edge in this place, we can talk about Internet of Things integrated with the cloud, and diverse demand applications, as I showed before, mainly using virtual reality, AR, that we have a video and big data traveling at the internet at high speeds. And AI and machine learning together unlocks the learning for complex patterns, adaptive control, autonomous operation, and Encoders extraordinary revenue. And open source enables collaborative communities, pre-standard specifications and code, accelerated progresses, and common tools in interoperability. Now, let us step by step we see the future is beautiful. And now let's talk about AI. First, what is required for AI? I select a common set of knowledge that is good to know to you get a more intensive development use AI algorithms. We can talk about calculus, about numerical computation, complex analysis, statistics, probability, information theory, algebra families, discrete mathematics, operational research, and also about geometry and basic algebra. Are very deep knowledge over here. Computer science knowledge, engineer knowledge, math knowledge. It's necessary to know everything about it to work with the AI. It's good to know. Today we have a lot of frameworks that you can use these algorithms, you can use this data, and you don't need to know everything about it to use AI. But it's good to know to get a more deep development, a more innovation development of you propose to work with AI. So this minimum set is good if you need to work more or you think about programming AI and AI solutions. This is a guide for you. AI, we have a lot of, it's a very big field indeed. We have AI like rule-based reasoning, it's a cloud of information. We have machine learning, it's a subset of AI like decision trees, logistic regression. Inside machine learning, we have a small set of Shaolin encoder, and the core, or a very small set in representation learning, we have this famous working of deep learning. That is the moment of the AI. Learning is everywhere. And how this works? The main core that they get a lot of attention is deep learning. The classical machine learning has this overflow. We define the problem, collect the data that we study in the problem, extract the features of the problem, then train the model and evaluate. Deep learning, that is the more interesting approach, we have a different overflow. When we define the problem, collect the data, and the neural network learns the features about your data automatically. In this kind of magic, I can say it's very beautiful because we are still learning about deep learning. It works, but we don't know why it works yet. And train the model, evaluate. So deep learning is this thing, it's very interesting. You have about a lot of breakthroughs involving deep learning. I got this timeline that I get in the NVIDIA presentation that shows for us. We can say 20, we have the Atari games solving by reinforcement learning. And then we have the ImageNet. ImageNet was a breakthrough very interesting because we have image recognition in the same level of the human can recognition something. So you get some person that is very trained in recognition some images. The ImageNet AI can equiparate or can achieve the same result that a human being can achieve. Also have the AlphaGo results that we have an AI winning from a human being. The conventional speech recognition, lip reading, and so on. Since 2012, deep learning achieved very interesting breakthroughs. And these breakthroughs are so strong that changed the way we think about AI. For example, before 2012, we have about ImageNet accuracy, about a low level of accuracy. And nowadays, we can say with a very good base and very good data, you can have about 100 accuracy. with not loss of accuracy here. And this is happening in all fields that you can apply AI with deep learning. Speech recognition, image recognition, and so on. And then we are living in a very interesting, revolutionary times, due to AI improving in amazing rates. So let's see some code examples. For these code examples, I use some TensorFlow examples. We're talking about Ouro. And these frameworks are very interesting to work with it. So let's step back and talk about linear regression. Linear regression is a meta application for you to get some data and learn about it. Create a function on a data describing this data. So in linear regression, you can use TensorFlow Keras models using the function sequential, and then create a layer, one layer indeed. This one layer is not a neural network, but it's a small function. When the first parent is one step and no activation function. So this is linear algebra, a function that achieves all my data with one linear result. And then, using Keras models, I can improve it. For example, using in this time activation function, the sigmoid. Sigmoid is a function described over this data set and this graph here. And then we can use my data, reduce, I apply a reduction over it. And my data now is over 0 and 1, creating a small set. And this, I can use a logistic regression to describe better my data. Also, I can apply another model like softmax regression, and now I use more layers. And this, I can describe better my data. So I can use 10 values. Each one is about 0 and 1. So I have a softmax activation. And in this time, I can use now a probabilistic description of my data. At the linear, I get a line that describes my data. And now, with this, I get 10 values using the softmax activation. And then my data can be described like a dense probabilistic one. And then, one step ahead, I can construct a neural network. We can see that using the Keras model, we just apply another layer. In this new layer, I apply another activation. Now I have indeed in my hand a neural network, a small one indeed. And then this second layer, I put a value like a small one that can be described by my data. I have 1,000, 1 million of points in my data. And then I reduce to this one and use the activation ReLU, a nonlinear activation function, use it to a very common one. I will don't enter in this field indeed, I just use it for illustrating the use of Keras. And then apply my previous one, softmax activation. Then using this layer with ReLU, I create the first step of a neural networks that reduces my 1,000, 1 million data to this small one set with 128. And over it, I apply my softmax that reduces to 10 values. In these 10 values, I have a distribution. My intention over here is that from my 1,000 or 1 million, my big data, I have this reduction that these 10 values of the distribution describes my data with a very good description, I can say. So this is an overview, very simple, very basic, how a neural network works. It's about functions, it's about approximation. So I have this big data, I don't tell what is it, I just tell this is about 1 million points, can be numbers, can be image, can be whatever, pixels, representation of sounds, and then apply this sequential model. The first layer, I apply reduction using ReLU, reduce to 128, and then the next layer reduce to 10 values. And now I believe that the 10 values, which one is ones between 0 and 1, describing my data. The next step, I can create a deep neural network, and then I apply new layers over it, changing the activation function. In this case, it's recommended to use ReLU. And then when I achieve more layers, I achieve the deep neural network, the popular one, deep learning. And the interesting effect over here that when I have the previous example where I have the big data and then I apply one layer and then the output with softmax, I can describe my data at the end of the softmax. But in the real world, I need to do a feature extraction of the data or get a better description with this, for example, 10 values. With deeper neural networks, at the moment that I put more layers, I don't need to do this feature extraction. The layers itself do this to me. And with more and more layers, more feature extraction happen in my data. Well, with this basic concept, we can now talk about the families of neural networks or the applications. When we call families, we call about our data, because I can say we have a lot of type of data, from images to time series to speech and so on. And for each type of data, we have each type of strategies applying from neural networks. So the first one, the deep neural networks, as the example that I showed before, we have our data organizing input, like a vector of numbers. And then the network is constructed about dense layers. So dense layers is like we have a lot of lines like before with ReLU or other activation functions, also with different sizes. And then we have as output and prediction. But that prediction must be compared with what we call about ground truth, or what we're expecting about prediction. So I'm looking for example, a regression. Apply the regression to predict the price of a house based in square feet, and the number of bedrooms, and so on. Also, by far, we can have a different type of data, and we expect some value. This expectation is called ground truth. And then, using feed-forward neural networks, the basic one, I compare the input vector, for example, the data about the size of the house, the location, everything that I transform in a vector of numbers, apply the neural network with dense layers, and then we get that probability result and compare it to the ground truth. With this comparison, then we can do the prediction over the data. Other type, very popular indeed, with neural network is the convolutional neural networks. In this type of data, we have the application of image classification. The input of these convolutional neural networks is an image. And inside of a data, we have the network with convolutional and poly layers. In this type of layers, we have a lot of layers doing loops, feedbacks. And these layers also are prepared to work with images. We have modules, hyperparameters, and other things that composes this network. And at the output, we have the prediction. This prediction, for example, classifies the image. So I can train a model of thousands of pictures of cats and dogs, and at the input, I can put an image of a cat or a dog. The output says which type of data or which type of semantic data we have in this image. The CNNs are the most, I can say not important, but on the more popular one, because we can see the results very fast. And this is where the AI is more used today. At the inside of a company or of the industry, in the industry 4.0, we have a lot of applications of CNNs like smart cameras, quality control, and so on. So we have a lot of good output in the prediction uses CNNs today. It's about approximately 100 of success in the identification of the input image. Due to that, we have a lot of applications of CNNs in a lot of fields in industry. An example of code in CNN, in this type we have use other function on 2D. In this type we have a small one, indeed. 2 lines that do the work of extract the features. Remember that in deep neural networks, the features are inside the neural network. With the 2 lines, for example, we do the extraction of the features. So we have an imaging input, like a photography of a cat or a dog. And then we extract the features. And then the next step, with the dense network, we do the classification of the data. And the input of the data is a previous one that we can call the training model, and the classification occurs over here. Another type of neural networks is the recurrent neural networks that are used to classify time series or sequence of data. So my input is different here. We have a sequence. The sequence can be a text, can be a speech, can be a video, and then the recurrent layers are trained to analyze the sequence and output the prediction. For example, sentiment analysis. We train a model with thousands of positive and negative sentences, and then we use the test as I put a sequence, and then the RNN classifies the sequence. Other types of applications like time series for requestings, a lot of applications in financial, prediction that use time series as input sequencing. A very interesting example is the Google Translate. We have the input sequence of a text in Portuguese, and then the RNN applied in Google Translate, translated to English or French or so on. And then we have a very interesting application of neural networks that called encoders. This one is very amazing indeed. It's very new. We have a lot of interesting results in it. And that's called encoder-decoder. We apply one of the previous neural network, like DDN, CNN, or RNN. Use as input an image, a test, a sequence, or so on. You have a universe as input. The encoder network is a step where we apply our neural network, the chosen one that you choose, and reduce your input data in a representation of the data, number or a vector of numbers, commonly a float number, a real number. And then that representation is applied in a decoder network. It's like we get a neural network, we do the inverse of it. We do the opposite. We get this neural network, put a vector inside of it, and take at the output a probably input of it. It's really a very interesting type of think about neural networks, because neural networks are mainly a math function. So I can put as input an image. The neural network transforms this image in representation, like a number or a vector of numbers, and the decoder do the inverse one. Take that number and creates an image. And then I can choose one network for encoder and other for decoder. I can create very interesting things. For example, a very interesting example, I can create an encoder that do a convolution neural network over an image. So I get this image of this guy surfing, and then create this representation in vectors, a flattened one that we call. And then get this representation and put inside of a RNN, recurrent neural network, that translates that vector representation to a sentence. Create, for example, expression like a wave and a man in a wave, a surf. And then my decoder translates that vector for a test. And then I can create, for example, a translator that reads an image and creates a legend or a sentence about this image. And then we can see the power of the encoders, because we can transform an image to a sentence and apply back, create a description of the image. And so on. We have a universe over it. We can use this to translate a test to an image also. We can do the opposite. We can have a test describing a scenario or environment, apply the RNN, creates the flattened representation, and then use a CNN. We create the image that is described by this vector. So encoders are very interesting thinking about creating data, because now we can say that AI not only classifies data, also can use to create data. And then we have a very interesting application of encoders called GAN, Generative Adversarial Networks. In this application, we have a very profound and deep knowledge about probabilistic statistics. As I said before, it's very interesting to know about math behind the neural network, indeed, because it's a very beautiful concept that we are seeing today. But also you can use some framework to apply without know, but it's very interesting to know about how everything works. And generative adversarial networks is something that we can look with very good eyes and very interesting eyes, because the GANs receive as input a random seed. We're not talking about image or sequence or speech, just a random number. And then we use it to feed a network called generator. The generator can be, for example, convolution neural networks that get that input seed and do proposition of an image. In this type of description of generative adversarial networks we call fake image. The random seed generates a set of pixels, and the set of pixels we can put in a bitmap and call it image. And then we have a second network called discriminator, also called as detective critics, that has input a real image, a real one. And then this discriminator compares this fake image with a real image. And then in this comparison, as we can say, the real image is the ground truth, the fake image is the prediction. The output is called real or fake. And then some magic happens over here. We can put these two networks to work together in adversarial way, do this name, generative adversarial networks. The generator creates a lot of fake images, thousands, millions of fake images. And we can adjust the random seed or the parameters of the network. And we can create not a fake image totally random. We can create a fake image of a face, of an environment, a fake image of a dog, a person, so on. We can adjust this fake image. And this discriminator compare here another data set that we want to work with, for example, person, a dog, or so on. You choose the image that you want to work. And then we have some magic happening at the output. We will achieve a result that we have a fake image that is very similar to a real one, but is not a real one, considering, of course, your database of real images. So we have achieved a point where these two networks convolve together, and then we have a fake image that looks like a real image, but is not a real image. It's not present in your data set. And this fake image is generated by the generator that generates a lot of images, and then the discriminator selects one that says, okay, this is fake, but it's very similar to the real image. So the output at the network, you have a point that a little bit real one. So you have an image that looks like real, but is not. And then we have a very interesting result with GANs. We create content. So with GANs, the neural network can create data using the random seed and the reference data model, which we call the real data model, and then a new one is created. And this, I call this the top of neural networks nowadays, because neural networks not used to classify, but to create. You can see about a lot of results using GANs. The deepfakes are very popular. The art using GANs, we have a lot of results over here about using GANs for create art. Indeed, it's very interesting to see. So now we get about the insides of a neural network. Just a little bit of math again. So neural networks, or a neuron of neural networks, is just a function, a linear combination of inputs and weights. It's about multiplication and sums. The inputs can be vectors, can be numbers, can be pixels, but all is binary. I'm talking about computers. Computers are binary, so the inputs are numbers. The weights also are numbers. The weights are the approximation of the function that describe a neural network. We sum, we get the inputs multiplied by weights and sum everything. We can use the activation function that do some work with this result of the sum. For example, the ReLU, the softmax, each activation giving to us a result. The ReLU get your number at the end of the sum, converges to a step function like 0 or the number that you're looking for. Others convert to a range of from 0 to 1, and so on. We have a universe of activation functions. And the output of this linear combination can be a number or a vector. So the neuron of the neural network is this simple math. I love to talk about simple math. The magic behind neural networks is just sums, multiplications. And then the fully connected network, the fully connected layer, we have a lot of neurons. Each neuron calculates a dot product. This dot product uses a matrix, and then we interpolate everyone. So the input of a function becomes the output of the other. The output of one becomes the input of others. So you have this very big set of sums, dot products, and so on. So look, we're talking about simple math. We're talking about logarithm, exponentials, or integrals. No, just multiplication, just sum. Then back into Keras, we can do this with math, like MATLAB or C programming, but if you're talking about frameworks, we can use this function. For example, create a instantiation of a model, take a sequential one, and create this linear model, a linear function. The first parameter in dense is the number of outputs that I want to get. I can get 1, can get whatever, 10, for example. The activation softmax. At the output of the sums, I can apply some function, softmax, like using the max number or maximization of the result. And then when we are talking about images, we're talking about pixels, and an image is just a matrix of numbers. So for example, having this input an image with 4 pixels, and then the neural network is just like this. We have the weights, or is a matrix. These weights are parameters represented in your numbers. We get the input. We can see that image with the results 12 and so on. You just put like a vector in input. We have the bias. This is just that you use in neural network to approximation. And then we have the output, that the scores. And then the scores are associated with classification. For example, the first number associates to a plane. The second number associates the image to a car. But what I want you to think about it, that neural network is just multiplication, is just sum. The concept behind the numbers that are the human knowledge about the numbers. So when we call about training a neural network, we are calling about this number represents a plane, this number represents a dog, this number represents a cat, and so on. But the math behind it, it's very simple. And then when calling about a neural network, we put more functions with more inputs. For example, the first line we have more dense layer with more numbers. And then our model becomes more deep. We have function of function. The linear model, we have a simple function, applying softmax over the multiplication of x, that x you can think about my input, and then the weights. And then the neural network, we get other function, it has input of 1. Então, so the neural network is just a function of function of function of function, and so on. In each function, we can use some different weights. And this function also is very simple. It's just, I will be very repetitive about it, because we have a plot twist at the end, just about multiplication, and sums. And then my deep neural networks is just the sequence of hidden layers or hidden functions. I put a lot of functions, one step another, and create this from the input layer. We can do a lot of layers. I can talk about hundreds of layers, thousands of layers, millions of layers, and get the output. And each neuron, remembering, we have a set of inputs, the weights, multiply each input by a weight, sum everything, and feed to activation function for some adjust to my result. And then, now comes the plot twist. Each neuron is very simple. It's a dot product. When we have M in a layer, each neuron, which input get this dot product, we have the result. And then we get all my inputs, we construct a very big matrix, create this representation of a system over here. We have this A matrix. A matrix are all my weights of my neural network. The X is my input and B is my output. And then we have this density operation. Because we have a matrix with size M and K, and then inside of our computer, we have a lot of operations. When you do this matrix multiplication, we have about M.K plus 2.K elements to move inside our memory. Our memory, the RAM of our computer, memory, the main memory. And M.K match operations. For our computers nowadays, our personal computers, smartphones, notebooks, and so on, this is a lot of computation. It's very simple computation, as I can say that from the beginning. But when we're talking about deep learning, deep neural network, we are talking about millions of millions. Our matrix get a size of 24 gigabytes of memory. And this is a lot of computation. So we have this plot twist. It's very simple computation, but it's very intensive computation. And then our common computers can do this in a resonant time. And then we need to use like a graphic process unit and new hardware to do this computation. And then the cloud becomes very important because we needed to use very big machines to do this. And it's very impressive need of the machines over here. For example, we have these new RTX GPUs from NVIDIA that can do a lot of computation, but you need to put in a computer 2, 3, 4 GPUs to do this. And then you need to get a lot of energy in your house or in your escritory to feed this one. So it's very interesting to think that it's very complex and very simple strategy to do neural networks, and also need a lot of machines to do it. And then the cloud becomes very important in the use of the neural network. And then you have very strategies like batch matrix multiplication. The TensorFlow language indeed is created to do the better manipulation from this matrix to the transformation from the vectors. So we have a lot of interesting strategies used by the companies. The Google use this proposed hardware, TPU, and the TensorFlow language to do the better manipulation of this simple math. And we are evolving to model complexity in rate explosion, because, for example, the Microsoft HasNet get about 6 million parameters. So my neural network has 6 million parameters. Nowadays, we are talking about billion of parameters. And do this model complexity is a very, very big thing. The generative adversarial network that I explained use a lot of computation, a lot of parameters. You need to get a big hardware to do this. So the cloud is the solution for this. And for an illustration, a very interesting illustration for you to see after my presentation, the TensorFlow Playground. It's a very interesting tutorial given by Google that you can play with the concept of neural network. You define some type of data, that the features, the input, the hidden layers, and so on. Without to do a single line of code, you can apply some knowledge of your neural network. You can configure the learning rate, the activation function, the regularization, and so on. The problem type that you use in your neural network. And this works in the cloud. It's a very interesting framework. The Playground is mainly for learning, but you can also use it to explore some applications of the neural networks to some problem that you are researching or working with it. So with this, I get to the end of my talk. I hope that I get you thinking about it, because my objective here is to get you guys to think about what I presented here, about the very interesting applications of the neural networks. We are getting a very interesting new world nowadays, and there is a very strong need to programmers to know about it, to work with it, and now to know the limitations of the use of the neural network. Neural networks are mainly simple math applied in an intensive way that will achieve some very interesting results. And behind the neural networks, we have this mainly fiction thinking about how the AI can conquer the world. The thing is more simple. You need to know more about math to use AI in a better way. So thank you very much.